Um, the restoring force is always opposite and proportional to the delta x. Um, and also it's a simple harmonic motion is like back and forth, and it's F equals to negative K delta x.
Hmm. Okay. And from this equation, delta x, remember, always is change in length measured from original length, right? And F here is restoring force. Restore to the original length, right? So remember, always point to the center. That's why we call it restoring force. And over here, normally you may see this kind of lab design questions, right? Peyton, Jaden, are you able to turn on the video? So you need to design a lab to find a spring constant. You have different ways. So first one, it would be hanging vertically. Hanging vertically. So you hang a bunch of different masses, right? When you hang different mass, it will be stretched different length, right? So you can plot mg versus x. You use a slope to find the spring constant, right? And for this kind of question, you will see you can use the area under the curve to find the work. Why? Because the force is not constant, right? And then you can use energy conservation, right? Energy conservation here. So remember, you can draw a graph when it's at equilibrium position, your kinetic energy will be maximum. When you stretch to the maximum position or compress to the maximum position, you will have maximum potential energy, right? So you can use the energy conservation to solve the problem, right? And over here, it's talking about this describing the motion when you go from A to O, O to B, B to O, and O back to A. So you all know that when you go from A to O, that's 1/4 of the period. 1/4 of the one revolution, right? And then you can set up this graph here. How to draw X versus T, V versus T, and then A versus T. You got it? So when you look at this X versus T, how do you know it's a cosine? How do you know it's a sine? It depends on where is your starting position, starting point. You see that? So X equals A cosine omega T, right? Now, if X is A cosine omega T is a cosine, then your acceleration has to be cosine too, but it's a negative because it's a opposite direction. Does it make sense? Now, if you know the maximum displacement, how do you find the maximum speed? You use the energy conservation. Maximum kinetic energy will be converted into maximum potential energy. Does it make sense? And then you can find A max, right? So you use net force equal MA. A max will be equal to negative K over MA. Got it? And the P area is 2 pi square root M over K. So you'll find omega will be equal to square root of K over M, right? So you remember P area does not depend on the amplitude. So if you stretch it to 10 centimeter, release, going back and forth, the P area would be the same as when you release at 20 centimeter. If the amplitude changes, the P area doesn't change. Why? Why? It's because when you stretch more, right? F equals Kx. Your acceleration is greater. That's why actually the further away you have greater acceleration, right? So the average speed will be the same. Does it make sense? You got it? Right? This part. So this is the spring situation. Then let's talk about the second part. Second part is the pendulum, simple pendulum. Okay? Simple pendulum. So you go down. What's a simple pendulum? It's made of a string. And string is hanging the ball. So we don't consider the mass on the string. We call it massless string, right? But the sphere, the ball here has a mass. So on the ball, you will have mg, you will have t, right? Then in this case, this is theta, right? Make sure you take notes, okay? I will help you finish the notes here, and then we will talk about a question, including rotational question too. So similar to spring mass, for the simple pendulum, it will oscillate between A and B. And when it's hanging straight down, that's the equilibrium. Okay? So in this case, what does the P area depend on? P area is 2 pi square root of Lady Gaga, L over G. Because sometimes you may mess up with the equation. You got it? Right? 2 pi square root of L over G. You got it? Does it make sense? Then your omega will be equal to square root of G over L. But normally, we don't use this one too much for a simple pendulum, right? Because omega equals 2 pi over T, right? And then another application you learned in working energy will be energy conservation. So EA equals
Wait,
E.
I have a question. So L is the length or what?
Oh, thank you. L is the length of the string. Length of the string. Yeah. Right? So if you look at EA equals EO equals EB. So when it's released at A, that's potential energy. Got it? And then when you add O, it's a half mv max squared. Right? And then when it's anywhere between, it will be half mv squared plus mgh. H, basically anywhere between, right? And do you understand here, this H is equal to the whole length? And then if you look at this part, let's L cosine theta. Got it? Mm-hmm. You got it?
Wait, is it 1 minus cosine theta?
Yeah.
Okay.
Because H here, you look at H here has to be equal to L minus L cosine theta, right?
Mhm,
Just take a common factor out.
mhm.
You got it? And then we'll see, show you how to do the questions. Bonnie, you have question here, right?
Yeah.
Mm.
Um,
Isn't this one?
um, no, it's
This one?
4 and 5
Or 4 and 5, okay? So 4 here, what kind of situation?
momentum.
Angular momentum, right? So this is a pivot. Okay, read the question. Read the question quickly.
A rod is attached to a pivot at one end and rests on horizontal surface as shown. Frictional forces are negligible. In figure 1, a puck is launched perpendicularly to the rod and makes contact at the far edge of the rod while traveling with a speed v. The angular momentum of the puck with respect to the pivot immediately before impact is L1. In figure 2, the same puck is launched again at the rod but at an angle of 30 degrees to the rod. The puck makes contact at the center of the rod while traveling with speed v. The angular momentum of the puck with respect to the pivot immediately before impact is L2. Which of the following correctly represents L2 in terms of L1?
So this situation, this angular momentum is created by point mass, right? When you are looking for angular momentum, you have two equations to find it. What are those two equations?
RmV square and I omega. I alpha.
Rp sine theta and I omega. I alpha is net torque. I
Mm,
alpha is net torque, is I omega.
mm,
Rp sine theta is applied for the point mass. I omega is applied for the solid object. You see that?
mhm.
So what is Rp sine theta?
It's the perpendicular to the rod.
Yeah, this one is a sine 90, right? So it will be L, the length of the rod, right? And then MV sine 90. That's L1.
Mhm,
It's L1, right?
mhm,
Then how about L2? L2, it tells you it's a half. MV, and then it's a sine 30. So what do you get? 1/4 LMV. This is LMV. That's why you will get D. Using RP sine theta. Did you use the wrong equation?
I think I use um I don't know. Because
Mhm.
I chose C before. I think I used the I alpha one because yeah.
Oh, use the wrong equation. Mm-hmm. I alpha is network. You
Mm,
got it?
yeah.
And then five. Five, what kind of problem?
Like kind of like collision.
Mm-hmm. So assume, right? Assume what kind of situation? This is a rotating plate, right? The platform is rotating, right?
Mhm.
And then the platform has M and R. The I is half M R squared, right? So immediately before landing on the platform, it has a horizontal velocity tangential to the outer edge. So this the mass of this object, right? Velocity is going this way, right? Tangential, right? Which on the following is equal to the angular momentum of the student immediately before. So it will be just, you are only looking for the angular momentum of the student about the axis before landing. So it will be R M V. You got it? Does it make sense? Mm.
Wait, but I th I thought the student and uh the platform is like one big object.
Oh, let's talking about after. But right now the question does not ask about the angular momentum of the system, including the student and platform. Right now, it only asks the angular momentum of this student before landing on the platform, right? And the question tell you, oh, it's going in tangent to the platform, tangent to the circle, right? And in landing on the edge, that's why you can use RP sine theta again, RMV sine 90. So
Mm,
when you read a question, be careful, pay attention to what is asking, right? I know in this question, there's another question can be asked. Oh, can you find the final angular speed? Then if this is not rotating initially, right? If it's not rotating initially, then you can get, oh, you use RMV. And then right now it will be half mr squared plus mr squared times omega. Then you can find the final angular speed too.
mhm.
Does it make sense? Mm. Go down. And then what other question?
Mm. Uh, and then 11.
Mm. So in this situation, right? The pulley situation, right?
Mhm.
So read the question. I don't know if the right the others, do you get to this same question too?
Oh, an axle passes through the pulley. Each end of the axle has a string that is tied to a support. A third string is looped many times around the edge of the pulley, and the free end attached to a block of mass MB, which is held at rest. When the block is released, the block falls downward. Consider clockwise to be positive direction of rotation. Frictional effects from the axle are negligible, and the string wrapped around the disc never fully unwind. The rotational inertia of the pulley is 1/2 mr squared about its center of mass. The block falls for a time t0, but the string doesn't completely unwind. What is the change in angular momentum of the pulley block system from the instant that the block is released from rest until time v t0?
The question is a key point, keyword. You are talking about net instant, the block is released, right? So in this case, you look at this question, and then you are looking for change in angular momentum. When you are looking for change in angular momentum, what can you use? What equation can you use?
Torque times time.
Yeah, you can use torque times time equals change in angular momentum, right? Then right now, the moment when it's released. So right now, we are going to use on the system, right? So the external force will be mg. Does it make sense? Right? In this case, you may get confused with the T here, right? But right now, you look at the whole system, right? The moment when it's released, you will assume T will be equal to mbg. That's why you are looking for the torque created by the gravitational force. So it'll be R mbg time delta T, torque time.
Wait, can you explain again, like why is it MB instead of like MB plus?
Oh, why? Because you look at the whole system.
Mhm.
What's the external force create torque?
MB.
Because in this situation, the tension will become internal force. Do you see that? The force applied inside the system, inside this pulley and block system, right? So the force creating torque only mbg.
Okay.
And then rotational center is here, right? Remember R, F, sine theta. R perpendicular to F. That's why this perpendicular arm length has to be radius. You got it?
Mhm.
Mm. Is it right? Do you have more questions?
No.
No, you good? Okay. So you continue to work on that. Mm. And then I can give you more. Any others have rotational questions? No? Okay. So rotation, do you need more questions? I think unit 6 and 5 multiple choice question you all have, you all already downloaded, right? Yes, right?
Yeah.
Yeah.
You all
Can you
downloaded.
send the answer key again of these?
Oh, answer key for which
There's
one?
answer key. I don't know. There's just like a lot of PDFs.
And not. So I don't remember what you have already, right? But let me look at it. I think you may have, I create another one, most recent. Let me check if any of you missing that one. It would be multiple choice questions, right? Multiple choice question. So you can download this one right now. And I put the answer key here. And then later, if you feel like, oh, you need more, let me know. I can create more. Oh, let me see which one I have. Did you download it? Down this one. 5 and 6 multiple choice question. I believe you guys all have it already, right? It's important to review the notes before you do the question. And then you summarize what we already did, right? Because if you finish all the questions I give you, this should be plenty. But remember, you summarize, oh, when do you use which equation? Why do you use this equation? Those kind of problem. You got it? You can download it. And then rotational momentum. Some of the packet you will see there are duplicate questions. Basically, it's going back and forth. And this one, momentum, angular momentum, it should be, you should get it a while ago. Yeah. So you can download it. Okay, so later, you can check it. If you have any question, you can stop me anytime. Now, let's talk about more questions here, okay? In simple harmonic motions, okay? So, now let's look at this question. I believe this question we didn't talk about, right? No. Bonnie, we didn't talk about this one, right?
I don't think so.
No,
No.
okay. Tatum, can you read the question?
Can you hear me? Okay. A sled of mass M is attached to one end of a horizontal spring with spring constant K as shown. The other end of the spring is attached to a wall. The sled is free to move along a horizontal surface with negligible friction. A block of mass 2m is placed in and secured to the sled. The sled block system is displaced a distance x initial and then released. Which of the following expressions is equal to the time the sled block system takes to travel distance 8x?
So try to see how to set up equation. What kind of problem? So what equation do you use for this one? What kind of question you are looking for? Try to look at the notes, right? This is spring question. It says that you are looking for the time for it takes to go through A8XO. In order for you to understand this question, remember this is arrest. And then assume this is XO, right? It's AOB. The under. Mm-hmm. You draw a diagram. So right now, how do you find how much time does it take? Pattern, what do you get?
I got C.
You got C? Okay. Let me see, huh? From the C to, okay. Mia, what do you get?
I'm still working on it.
Okay. Nana, what do you get?
I got C.
C2, right? Pattern, can you explain how you get C?
Isn't I think it was like T equals to 2 pi squared 3m over k.
Okay.
But then so if you for it right now, when it one period would equal to 4, like 4 x traveled, right? The
Yeah.
1, 2, 3, 4.
Mm.
And so for it to travel 8, you just have to do it again.
2T, right?
2t, yeah.
Yeah. 2 times 2 pi square of 3m over k. Okay, that's good. So this is the brain. And then this one, I think. Let's do FRQ. This one we didn't do it, right? Last time, right? So let's do this question right now, okay? Mia, you can read the question.
A small sphere of mass m is suspended by a string of length L. The sphere is made to move in a horizontal circle of radius r at a constant speed, as shown above. The center of the circle is labeled point C, and the string makes and theta 0 with the vertical. Two students are discussing the motion of the sphere and make the following statements. Student 1, none of the forces exerted on the sphere are in the direction of point C, the center of the circular path. Therefore, I don't see how there can be a centripetal force exerting on the sphere to make it move in a circle. Student 2, I see another problem. The tension force exerted by the string is at an angle from the vertical. Therefore, the vertical component must be less than the weight mg of the sphere. That means the net force on the sphere has a downward vertical component, and the sphere should move downward as well as moving around in a circle. What is one aspect of student one's reasoning that's correct? What is one aspect of student two's reasoning that's correct?
So A, try to see student 1 and 2 statement. Which one is correct? Mm. Student 2, right? Bonnie, what do you get?
Okay, I think student 2 said the vertical component must be less than the weight mg of the sphere is correct because it's actually cosine. Cosine L theta.
Mm.
And then yeah, it's not directly. And then but it says the sphere should move downward as well as moving around the circle. I don't think that's correct.
Mm-hmm. The vertical component of the tension should be equal to mg, right?
Oh. Yeah.
Yeah, and then net force is the point horizontally to the center, right?
Mm-hmm.
Yeah. So that's correct. What you mentioned. Oh, this reasoning you talk about vertical component must be less. That's incorrect. Then how about student 1? Student 1, which aspect of the student's reasoning is incorrect? Mia, what do you get?
I think student 1 saying that there isn't a centripetal force that's exerted on the sphere, that's incorrect.
Oh, there's a centripetal force. Okay, but if the student saying that, I don't see how there can be a centripetal force, right? The
Yeah,
student
so I
saying that
think
it doesn't have, yeah. Mm-hmm.
yeah, so I think that's incorrect.
Okay, good. Uh-huh. Adana, what do you get for both?
For the first one, I said that the second part of what he said, how there's no centripetal force, to make it a circle is incorrect because there's a horizontal component in the tension. And then
Mm.
for student 2, I said that um that the vertical component must be less than the weight of mg is incorrect because it's equal.
Mm.
And then the second part's also wrong because of that.
Okay, thank you. Okay, so let's continue to talk about B. You need to derive the equation and then use the equation to describe your reasoning in A. Now we can set up equation. Centripetal force and net force in what? You remember? That's a part of conical pendulum. Uniform circular motion, right? Do you remember? I'll put it here. You have mg going down. You have tension going in a direction slanted, right? This is x. This is y, right? That's a tension, right? And then this is theta O, right? So it will be net force y equals 0, will be T cosine theta O equal mg. T sine theta O equals, what is given here? Fs, right? Basically, it's mv squared over r. But you are looking for net force. So what is the net force? That's the net force in x. So from here, you can find T. Mg over cosine theta O. You plug in. So you get mg tangent theta O will be equal to net force x. So 2i, you can explain it, right? So you can see, oh, how do you describe one aspect or step in your equations, in your derivation here? Link to your answer in either AI and A2I. You can link, right? So the net force in the horizontal, this net force is in the horizontal direction, right? Which is the horizontal component of the tension. That's indicated in AI, right? And the tension here is mg over cosine theta. So you know tension is greater than mg. Let's describe to A to I. Does it make sense? You got it? Done right? Does it make sense? Over here. Yeah, this is conical pendulum. Now it changed to simple pendulum. You see the difference? Conical pendulum is doing horizontal circle, but simple pendulum is just oscillate between those 2 points. Oscillate between A and B. This is your O. It's going back and forth here. Got it? Earlier it's a horizontal circle like this way. So don't get confused between conical pendulum and simple harmonic, simple pendulum. So right now, second part, right? Now you can read through the question.
Instead of moving in a horizontal circle, the sphere now moves in a vertical plane so that it's a simple pendulum, as shown above. The maximum angle delta max that this theta max that this string makes from the vertical can be assumed to be small. The graph below shows data for the square of the pendulum period t as a function of string length L. On the graph above, draw a best fit line for the data, then use the line to calculate a numerical value for a gravitational acceleration g.
So this, how do you use the graph to find the acceleration? How do you use that? Try to see how you use the graph to find the acceleration.
Is it the inverse of the slope?
So what's the equation? Would be t equals 2 pi square of L over G. So you get t squared equals 4 pi square over GL. Then did you guys see? This is a very common lab data analysis in this chapter. You do t squared versus L, right? For the spring mass, it'll be t equals 2 pi square of m over k. So you get t squared equals 4 pi square over k, and then time mass.
Wait, I'm kind of confused. Why are we squaring?
Oh, you need to find a linear relationship. If you don't square it, then it would be square root. The curve won't be a straight line, right? So if you do T versus L here, it will look like this way. When you get a curve, it's very hard to know the relation. So in order for you to find a relationship between T and L, or between any two variables, always you need to linearize. We call it linearization. You got it?
Okay.
Mm. And then this one, right? This will be T squared versus M. Does it make sense? Sometimes you will see this kind of multiple choice question too. Got it? Oh. And then what you need to do, you draw the best fit line. First, you draw the best fit line, like a mean value, right? Then remember, you need to physically show, pick a 2 points on a line. You pick a 2 points on a line. So it'll be y2 minus y1 divided by x2 minus x1. You need to physically show the work. And then remember, pick 2 points on a line. It's not data point. Especially when data points are not on a line. And you will see that this situation, it has a unit, right? So you find the slope, you set this slope as 4 pi squared over g. So you use the slope to find the g.
Wait, so is the slope spring constant?
Oh, in this question, it's pendulum, right? If it's a spring mass, it will be 4 pi squared over k, right? I just give it, in some situation, it may be given this way. But this question, we don't use this equation right now. You only use this one for spring mass.
Okay.
Does it make sense? Right? Yeah. So this is similar question may be asked. Good. Thank you. Right, keep asking any question you have. So far, so good. And then remember, when you get the answer, don't forget your unit. Always check for unit. And then for the K, right, spring and the slope here, everyone should get slightly different value in a certain uncertainty range, basically. Okay, now let's look at D and E. You can try to see how to do this question quickly, right? So what do you get from this one? So remember, theta maximum is here, right? And then when you go to theta equals 0, it's in the center. Theta equals 0 will be here, right? This maximum is here, right? And this is a negative theta maximum, right? So remember that. So you will go from positive theta maximum to negative theta maximum. You guys download these questions already, right? Let me know if you need to upload it here.
Wait, can you upload these to Google Classroom?
Okay, Later I can upload in that too. Google Classroom there's a limit there. So let me see. I can get rid of some of the others. So how do you draw potential energy? Change it over time. Once you get ready, let me know. Okay, so this is the maximum, 0.5 times minimum, and then 1 maximum. That's good. Any other answer?
Wait, no, it's wrong. Sorry. I'm gonna change it.
0.5 is here, right?
Yeah.
Is it in this case? If this A, this O, 0.5 will be B, right? And this is a 0.25, right?
Like this,
Mm,
maybe.
yes.
Okay.
So you can tell when you get to A, maximum potential energy. When you get to B, maximum kinetic energy. Oh no, maximum potential energy. And then at O, there's a noise point. So your potential energy is where? At O. At O is 0.25. That's a theta equals 0. That's why potential energy is minimum. And then when you get to B, maximum again. Got it? So you are realizing this situation, potential energy cannot be negative, right? Because at the lowest point would be potential energy equals 0, right? Does it make sense to you? Okay, then let's do E. So far, so good, this question? Okay, let's do E. So E, right? So over here, when the sphere swings back and forth, it must also rotate a small amount in each string, right? So over here, I give you, so when it's going this way, it's rotating. When it's going this way, this is in a rotational direction. But when it's going to the right, that's your rotational direction. Did you see that? So try to see how do you find the direction of torque.
is it clockwise?
On the talk has to be clockwise. Why?
Because initially spinning counterclockwise, but when it goes to the left, it turns to clockwise.
It changes from counterclockwise to, so when it's released from here, it was counterclockwise. And then when it come back, it become clockwise. So the torque must be clockwise, right? And then, and the maximum displacement, what force give you torque?
Opposite direction.
Huh?
Opposite direction.
Opposite direction, but which force? Which,
Force, like linear, yeah.
this would be gravitational force, right?
Yeah.
So your gravitational force, when you get here, right? When you go down, gravitational force. When you get to the left end, gravitational force create a clockwise torque. Got it?
Mhm.
Mm. Thank you. So that's the question, FRQ question. For the pendulum, conical pendulum, all we need to know about it. Now let's take a 5 minutes break, right? If you need to use the restroom, you can go right now. Then we'll continue, okay? Mm.
Two.
What do you mean? You have a graph to represent the horizontal component of the block's acceleration. Is it graph two?
Oh, graph two.
Is it
Wait,
graph?
no, I don't think it's graph two, but
Mm.
I think it's graph one. I don't know.
Mm.
Graph one.
Why is it graph one, not graph two?
Because it's acceleration.
It's acceleration, and then on the x-axis is the position, right?
Mm.
What's the relation between A and X?
Um,
Mm. What's the relation between A and the X?
A equals negative K K over X.
Yeah. So theoretically, A versus X should be a linear line with a negative slope.
Yeah,
Why is it negative?
because it's opposite direction.
Mm. Okay, good. So what is A? Because in this situation, you are talking about a magnitude, right? Theoretically, this path would be going down. It's a magnitude, so you use the absolute value. Very good. You good? Then B, how do you answer? Oh, we didn't finish this one. So graph two represent a momentum, right?
Oh, why?
Mm. Why momentum is not
Wait,
straight line?
um, I thought this situation don't have momentum.
Mm. Momentum? Why it doesn't have momentum? What does momentum depend on?
Mass and velocity.
Yeah, if you don't have momentum, why? Is it because it doesn't move? It doesn't have velocity?
Mm,
Hmm?
no, so that one is, so graph 2 is momentum.
Mm. So why momentum is not a straight line? The velocity is not linearly proportional to to x, right? So you all know that when x equal O, it has a maximum kinetic energy. It has a maximum momentum, right? So when at negative d, positive d, that's zero, velocity zero, momentum, right? You got it?
Mm.
You done?
Yeah.
You good?
Wait, for graph 1, why is the acceleration and the position like, can you explain the relationship between acceleration and position on ramp again?
Yeah, so it's this one, right? MA equals a force, swing force. And then swing force equals a negative KX, right? That's
Oh yeah,
how you get A equals a negative K over MX. But right now you are looking at the absolute value of it. So you'll get K over M absolute function of X. The
okay.
magnitude, the component of it, the magnitude of the horizontal
Okay.
component of the block's XL.
Yeah.
Does it make sense?
Yeah.
But velocity is non-linear, right? You can see, that's why we analyze the motion. When you go from A to O, B to O, is speeding up. So you are known at O, at point O, that's where you get maximum speed, maximum kinetic energy, maximum momentum, right? But at A and B, V equals zero. Zero. That's where you get maximum potential energy, elastic potential energy. You got it? And then C, Mia, you can finish reading the question.
Graph 3 above shows the total horizontal distance traveled by the block as a function of time as it completes two oscillations. Using the graph, determine the distance d between the midpoint of the ramp and the maximum position of the block on the ramp. Explain how you arrived at your answer.
So pay attention to the key information given in the question. When you read the question, what is the key information? Mm-hmm.
Can I see the graph again? Yeah. Oh, wait, no, the graph 3. Yeah,
Mm.
thank you.
You need to look at here, right? D to negative D. Did you download this package too? So that you can see on your screen too. Mm-hmm. Mm. So what do you think? What's a key point for this question? I didn't see you put here. So what's a key point? Does it tell you it complete two oscillations? Two oscillations, right? Two oscillations. If you look at this graph, what is two oscillation? What's the distance it will go through? This is basically you estimate using the horizontal distance, right? Horizontal distance. If it's two oscillation, it will be. It's similar to the question, multiple choice question you did, right? What do you get? So if it's one oscillation, it will go through 4D. Okay? This is 1D, 2D, half, 3D, 4D. One oscillation is a 4D. So two oscillations, two revolutions will be 8 AD. Right? Right? And then it tell you the total travel distance is 12. So you will get D equals to 12 over 8. Does it make sense? That's the information you need to use. Right?
Wait, so how do you know if 8D is 12?
Oh, in the graph, the total distance traveled,
Mm,
right? And it tell you it complete two oscillations, two revolutions, right? That's why you need to need to look at the diagram here.
okay, then why is it? Oh, okay, okay.
Okay, now how about D? D, Bonnie, you can read the question.
D. Suppose the entire setup was moved to the moon, where the gravitational field strength is less than that on Earth. The center of mass of the block again oscillates between x equals -d and x equals +d. Will the period of the block's oscillations of the moon be greater, less, or equal to the period of oscillation on the Earth? Justifies your answer.
When it's moved to the moon, what happened? What changed?
Gravity.
Hmm? Gravitational field change, right?
Yeah.
Gravitational field change, right? Then does it affect period? Will it affect the period? So analyzing this situation, what force giving you this acceleration? What force giving you restoring force?
Is it potential energy? Oh, I mean like the gravity.
Hmm? Gravitational force, right? Yeah. So in this situation, when you move to the moon, will it change the period? What do you think? The period will be greater or less? What do you get, Nana?
I was thinking less at first, but then if you use the equation with t equals 2 pi square root d squared 2h over g, over 2hg, and then if g decreases, wouldn't it increase?
Oh, but this is E, right?
Oh,
This is this is a E, right? But yeah, sometimes if you get confused, you continue to read through the question. Then yeah, this equation give you an idea how to solve this problem, right? But what happens if it doesn't give you, it didn't give you the equation, right? So that's why you have to analyze what force giving you this restoring force, right? So you'll see that when you move to the moon, you know G change, right? G is smaller, G decrease, right? Remember, G on Earth is 9.8 Newton per kilogram. But what is G on moon? You go to the moon, G on moon is around 1.6 Newton per kilogram. So you weigh less when you are on moon, right? So in this case, when you go to the moon, the period will be greater. Why? Because G is getting smaller, right? So the acceleration is smaller, the average speed will be smaller. But it's going through the same distance, that's why it will take a longer time. is greater. Good. And then E, you use an equation, right? But remember when you answer D, you're supposed not to use the equation at E, right? Actually, you use E to confirm what you get for D. So is it consistent? Mia, how do you answer E? Mm-hmm.
It's consistent because because G is in the denominator.
According to the equation, right?
Yeah.
Good. Does it make sense? So according to the equation, G is in the denominator with the smaller G greater T, right? Okay. So now let's look at this part. So you see need to track. Track 2 right now. So track 1, that's a situation you ignore friction. So for most of the time, simple harmonic motion, you ignore friction. That's why energy is conserved in both the spring mass and simple pendulum situation, right? So right now, there is a friction. Similar track, right? But there's a friction here. So x equals negative half d in this location. At time t1, actually is going up the ramp. At time t equal t2 is going down the ramp. That's the direction of velocity. Right? So right now you need to analyze the force. So how do you do this question? So remember it was T1, T2, right? Try to see how to compare in this case, right?
Wait, can I see the graph again? Okay.
So which location, which time, the magnitude only, the tangential acceleration is greater.
Is it at T1?
P1. Why is it at T1?
Because in T2, the acceleration is less because it already lost like the speed from friction.
Loss speed from friction, okay. And then how about second one?
Mhm.
You don't compare apple to pear, right? You cannot compare friction to speed, right? So what do you mean loss speed from friction? The second situation, does it also have friction?
Yeah, but doesn't it lose kinetic energy to it?
What do you mean? So in the second situation, friction doesn't reduce the kinetic energy?
Mm-hmm.
In both situations, both friction are in opposite direction. Both friction does a negative work, right? Right? This at T1, we going this way. At T2, we going that way. So both situation friction is going opposite to the direction of motion. Both situations, friction does negative work, right? But how do you compare acceleration? Acceleration is net force, right? Net force equal ma. At t equal t1, both component of mg and fk, they are going in the same direction, right? So you add it in opposite direction, right? But at T2 is mg minus fk equal ma. At T1 is negative mg plus fk equal ma. Did you see the difference? That's why at T1, yes, that's correct. The magnitude of the acceleration is greater at T1 because both parallel component, the component of gravity is a non-track and the friction, they are in the same direction. So the magnitude of acceleration is greater at T1, right? At T2 is the net force will be mg sine theta minus friction, right? So the component of the gravity along the track is in opposite direction to friction is subtracted. That's why it's smaller. You good? Does it make sense? You done? Done, right? Okay. So there's another question you can do it yourself as a homework. It's similar, right? Similar to the question we talked about. And let's do a spring question. Spring question, let's look at this one first. Bonnie, you can do the question?
A group of students must determine the spring constant K of a spring that hangs vertically from a ring stand. The students attach a block to the bottom of the vertical spring, as shown in Figure 1. The students then pull the block spring system 0.5 meter below the system's equilibrium positions and release the system to that it oscillates. The students record the mass m of the block and the period of oscillations t for several trials as shown in the table. The student wants to determine the spring constant at k of the spring.
Mm-hmm. So how do you draw it? What is on x-axis? What is on y-axis? So what is on vertical axis and horizontal axis? After we did last one, this one should be easier, right? Peyton, what should be on the vertical axis and horizontal axis?
Like from the graph from the table above.
Mm-hmm.
Hmm. Would it be mass and time or
Mm.
I'm not sure.
Okay. Then try to see, how you are looking for K, right? In the table, what is given? What you are looking for, right?
Mass the vertical and time the horizontal.
Oh, we want to put mass on vertical, time on horizontal. Okay. Thank you. Mia, what do you want to graph? Mm-hmm.
Is it like I can only choose like M and T?
Your variable is mass and T.
Yeah.
Mm.
I think the same.
Same.
Yeah.
Okay. Bonnie, what do you choose?
I think the same too.
The same. But remember, pay attention to what is asking. It says that which quantity to be graphed to determine spring constant by using best fit line. That's the key. It's a linear line. If you use a mass versus period, it's a linear line. Mm. It's a linear line. No, right? Equation. Look at the equation. What equation is related to mass and period. What equations? Which one do you look at? Remember, you are given T, you are given mass, right? So what equation?
T equals 2 pi square root M/K.
So T equals, I'm going to use this one. T equals 2 pi square of M over K. Is it linear relationship? No, right? So you need to linearize it. 4 pi square over K M. So instead of using T versus M right now, is you use T square versus M. You got it? So should be, you can use M versus T square or T square versus M. Either one, right? Okay, and then you are going to draw the best fit line, right? Just remember you use scatter points. So it will be T square, second square versus M kilogram. Remember, you put a unit. And in this case, your measurement, you only measure mass and period, right? That's why you need to calculate T square. You are given extra column, right? You got it? Does it make sense to you? And then we can continue. This one, you can do it yourself later, right? Just remember, you do the scatter point. Don't connect the dot with the line. And then you draw the best fit line. You use 2 points on the line to find the slope. And you set slope as 4 pi square over K so that you can find the K, right? Then look at the second part. B. B, how do you answer?
No.
Mm-hmm. The answer is no, right? Is it no? So how do you justify? State your reasoning.
So amplitude doesn't affect the period.
You change it horizontally or you change the amplitude. The period does not depend on amplitude, right? Only depend on mass and spring constant. So you need to mention it has the same mass and then the spring is the same. So spring constant is the same. That's why the period should be the same. Okay? Did you write down? Make sure you redo this question later, right? Now, how about C? Mm-hmm. So how do you write the procedure for this one? Right? So remember, we talk about this spring lab design question, right? One way you can use net force equals 0 in this situation, right? You use net force equals 0. So mg equals k delta x, right? Another way is you use a period. You can measure the period to find the spring constant. That's another way, right? So see here, just remember, you need to describe procedure, right? To find whether or not the period for both situation won't change, right? Compared to each other should be the same theoretically, but you need to prove it. And then remember, you also need to include steps necessary to reduce experimental uncertainty. You know what it means, right? Repeating always. Any kind of experiment, lab procedure, you always need to repeat. Okay, so how do you write this one, right? Peter, you can answer this question quickly.
Yeah, for C, can we just like run both the horizontal spring and then the one dangling, and then just time how long it takes to do like two like oscillations or like two periods, and then you can use that data and see if they're equal or not.
Oh, did you give enough detail?
Uh,
So you use meter stick to measure the original length of the spring, right? This is horizontal one, right? And then stretch the spring point a meter from equilibrium, right? And then release the system from rest, right? You also need to give it detail, right? When it's a stretch 0.8 meter, because this 0.8 meter, right? From the equilibrium position. So use the stopwatch to measure the amount of time it takes to oscillate 5 times, 5 oscillations, right? And then repeat 3 times to get average, right? And then you will find a period. You compare the period to the first situation. Does it make sense? Does it make sense to you? Mm-hmm. Any question here? Always, for any measurement you have, always you need to repeat, okay? Now, did we talk about this question last time? This one? The spring one? This one we didn't, right? So let's read through this question. Nana, you can help read this question?
A block of mass m is attached to an ideal spring whose other end is fixed to a wall. The block is displaced at distance x naught to the left of the spring's equilibrium position, as shown in figure 1. The block is then released from rest and oscillates with negligible friction along the horizontal surface. While the block is oscillating, it has a maximum speed of Emax. The energy bar charts in figure 2 represent the spring potential energy U of the block spring system and the kinetic energy K of the block as the block passes through the positions x equals negative x initial, x equals 0, and x equals positive x initial, while the block oscillates. The chart at x equals negative x initial is complete. Draw shaded rectangles to complete the energy bar charts in figure 2 for positions x equals 0 and x equals positive x initial. Positive energy values are above the 0 energy line and negative energy values are below the 0 energy line. Shaded regions start at the dash line, representing 0 energy. Represent any energy that is equal to 0 with a distinct line on the 0 energy line. The relative height of each shaded region should reflect the magnitude of the respective energy consistent with the scale shown.
So over here, first understand what is this question about, right? Understand it first.
At zero, is it just kinetic energy has everything and then the potential is zero?
Yeah. So
And then-
basically using energy conservation, right? Use the potential energy be zero, right?
Mhm.
And then XO,
Um,
negative XO here, positive XO here, and kinetic energy go to zero, right?
mhm.
Does it make sense now? This part? Using energy bar or energy graph is the same, right? Now, this one may be a little bit more complicated when you look at it. How do you determine the expression for a spring constant? Bonnie, you can read the question.
Using figure 3 and 4, determine an expression for the spring constant of the spring.
So how do you find a spring constant? What equation do you want to use? Look at the graph. What is it given here? What is it given here? Remember, every time you are given a graph, be careful, make sure you read through the key information, right? What is given, what you are looking for. So what do you think?
half over m or force
Huh?
over distance.
Yeah, because you are given maximum amplitude here, and then you are given maximum force, right? So you can use F equals K delta X. Then F max will be equal to KXO, right? Remember, you do have a negative. Negative is used to find the direction. So in this case, you are going to use absolute value. Because K cannot be negative. K is always positive. You got it? You got it? Then how about 2i? How do you derive the equation to find a mass? Find a mass. Which equation do you use to find a mass? This one may confuse you. So you use T equals 2 pi square root of M over K, right? From this graph, can you tell me what's the period? Mia, what's the period?
The period is 2 TO.
UTO. 2TO. And then you find K already, you plug in, then you can find mass, right? You good? Now, how do you draw V versus time? I want you to see both graphs. So Peter, how do you draw V versus time graph? And then there's another part here.
For the graph,
You are
what
given position versus time. How do you find V versus time?
well, would it start at 0 and go
Mm.
positive?
Or start from 0 and then go positive or negative?
Well, it's initially displaced negative, so we going towards the positive side.
Okay, then where does it get to the maximum V?
Like in between T0 and 0, like the half point, or
Yeah, right? That's
yeah,
when you get to the maximum slope, right?
yeah,
And then get TO, the V will be 0, right?
yeah.
It will be 90 this way, right? Yeah. Does it make sense? That's all good, right? That's a V. And then if we ask you to draw acceleration, you also need to know how to draw acceleration, right? So over here, this is the graph. Do you see that? We may need to come back, check this graph again. Now look at this question. Look at D here. This is a free body diagram of the object. Now it says that the free body diagram shows the force exerted on the block at T equals 1.5 TO. That's a student's claim, student's statement, right? So you need to see if this is consistent within the graph. As you sketch in part C. Part C is here, right? Where's the 1.5 TO? Is here, right? 1.5 TO is here, right? Where is it? When you get negative maximum speed, where? When you get maximum speed, it's normally in the equilibrium, right? That's why you cannot have Fs. You agree? Right? So horizontally, your net force will be 0. You get the spring force going to the right. That's why it cannot be T equals 1.5 TO. 1.5 TO, where is it? You will see, you either using the position versus time graph, you will see 1.5 TO is x equals 0. So it should be at equilibrium, any original name. Does it make sense? You got it right? You got it right? Mm. You done? Mm. Okay. Did you write out everything? So this week, you can first review all the questions we talked about. If possible, finish those multiple choice questions. It's okay. You need to do more, and then next class, I will help you go over 2 more FRQs, and then will be unit 8. I think your last exam, last test will be both unit 7 and 8 together. So we'll do it. Okay? So that's all for today.
Sorry, can you go back to